I'd like to welcome you all back to the afternoon session. This is session 3, and we're looking at what are the implications of 5G and EMF limits for the 5G network rollout. We have 4 of the ITU and standards experts up on the podium who are going to make presentations this afternoon. And we also have a remote presentation from my hometown in Melbourne, in Australia. I think it's just gone midnight, so I hope Jack Rowley is still awake. But unfortunately, Jack, you're at the end, so you need to listen to the others. But we might see if we could slot you in second if to keep things moving. But we have Jafar to kick us off while we check on the remote. So the biographies are all available online and in your handbook. If I read all of the biographies out, that would be the allocated time for each of the presenters. So I'm just going to announce who they are and invite you to check the biographies. But Jafar Keshvari, and Jafar is presenting on behalf of Huawei. So I'll hand it over to Jafar.
Okay, good afternoon. Regarding the talk that I'm going to make, first of all, thank you for the organizers of this very useful and good workshop for inviting me to have this talk here. The morning session has given a good background to the discussion that I'm going to make. I'll be more focusing on the standardization aspects, both the exposure limits, which ICNIRP had already talked, but leaving some challenging questions aside, and also the compliance assessment standards. The bigger challenge here is the PowerPoint slides, which we don't have, and unfortunately the other one, so I will use this traditional way of handling it, and hopefully it will not disturb you in not taking your focus away from the discussion. So let us look at the content, what I'm going to discuss. So we have a short time, 10 minutes. I will try to cover just a general introduction already is made, fortunately, regarding 5G technologies. And the challenges into mobile broadband growth we already have, and the reasons will be soon revealed there, and millimeter wave EMF exposure and compliance assessment standardization, as already mentioned, but I will list the challenges that we have in those standardization activities. What is worth to look at, already we had in the morning more attention taking this pointer. It's not that dangerous, but very powerful. So please note that although 5G spectrum, there are already exposure limits, existing ones, they already cover that range. It doesn't mean that although the millimeter wave has not been the focus and we haven't had that much technologies around, but please note that there are existing frequency region where we already have, and there are operating technologies already in that region, 4G, 3G. But it was good to have also mentioned about sub 1 gigahertz frequencies where we will be having some free bands to be used for 5G technologies. But please note that although it is the terminology used for differentiating the microwave or RF frequency region, the millimeter wave is the one that is specifically both compliance assessment standards and exposure limits standards at the moment are focusing to. So I will be focusing more on that discussion. I chose few slides. I like the slides from Intel. So we have, so I don't have any separate reference, so they are provided by Intel Corporation. So the reason whenever we talk about 5G technologies or from 1G to 5G, I just myself consider a kind of tube with different diameters. How you're going to use that amount of capacity, that is your what I called it, science fiction, or your imagination, what you can fantasize in your brain. So that is the opportunity which gives room for many endless kind of applications. So here are some examples to see, for example, in a connected factory, you can have 1 million gigabyte per day data exchange. In a smart hospital, for example, 4,000 gigabyte per day. So those are good figures to give some kind of understanding what kind of diameter we are discussing about. And here is another picture. So the application areas may vary from very different areas, the farming that you mentioned, to a very virtual reality is possibly one of the areas that is well advanced, and I would assume that 5G is going to be used, or virtual reality is one of the main applications that is going to use this opportunity. I intentionally took this, although this is the airport security checks, which most of us encounter daily, is not a 5G technology, but it is using the millimeter wave frequency in screening the body. So I just took as, you read that it's not a 5G, but still a 5G region or millimeter wave technology used for that technology. But another maybe 5G technology, which is already there, the technology and trials, is the massive MIMO technology. Our colleague from Ericsson will touch about that a lot, but we have, you see, what kind of configuration and some challenges in with regard to compliance assessment, which Christer Törnevik will discuss about. So let's move to. This is, I didn't have the reference, but maybe I should put it. So it is, this slide is provided by NTT Docomo. So there is, you notice that 5G experimental trials are being started already in Q4 of 2014. And there are many industry listed here. You see these chipset manufacturers as well as the handset and infrastructure manufacturers in the list. So challenges in mobile broadband growth. So this is something which there is a typo which was on the next version fixed broadband. So here you see we were discussing about the exposure levels. And this sets quite a challenging situation. If you look at the next slide, for example, the distance. Now you had 800, 900, 1800, 2100, and 2600. You see this is using the existing compliance assessment or the zone distance assessment, you will reach at this distance. Now adding a few more, then this is the distance. For massive MIMO, you get this 21 meter. So it is quite a challenge in increasing distance when you have different technologies added in the same base station. Now, let's move to the actual part of the discussion, which was related to millimeter wave EMF exposure. One of the key messages that I would like to remind here, which seems to be forgotten, although we all the time are discussing about, is to remember that we are talking about non-ionizing radiation. Although a very clear fact, but that is a fundamental issue when dealing with the non-ionizing radiation, what scientifically we have taken into account. And usually I give the example of photoelectric effect, which most of those who have been in the college or in the high school, they remember that that is the scientific phenomenon which Einstein was awarded the Nobel Prize. So the photoelectric effect simply it tells you that if the photonic energy, the electron volt, is not enough, you cannot detach an electron from the atom, from the molecule. If you cannot, even though if you increase the intensity from whatever level, you can even melt the metal, but you cannot detach electron. So that is fundamental issue to understand when we discuss about non-ionizing radiation, that you don't have enough energy to achieve detachment of electron. Now we have EMF exposure limits. As you know, two main organizations are dealing with that. ICNIRP was already introduced. Another one is IEEE ISIS. And I quoted this information that Mike mentioned about 350 papers, which can be found if you search for millimeter wave. But here we should remember that the standards, both ICNIRP and IEEE, they are covering from 0 to 300 gigahertz, which means that at the time when they were developed, they were taking into account also millimeter wave, which is 5G. So 5G, the name is new, but the old EMF exposure limits related science has been there. So it doesn't mean that there is something new as such. And at that time, 1,300 peer-reviewed publications was used for regarding the RF exposure limits at IEEE site, which most of the, I would say that literature, both in ICNIRP and IEEE are the same, and we should recall that at IEEE, the first world EMF exposure limits and the standard, they were developed by IEEE. So here we have the ICNIRP guidelines as well as IEEE. They are under revision, and fortunately they are going to be ready by the same time almost, by the end of. So this was my guess, but ICNIRP representative's presentation confirms that these estimated dates are correct. So, but IEEE and ICNIRP, they are doing the same. So we have different levels at different countries, which are not good, because if we have one science, which is the basis of all, they should be somehow harmonized. These are the list of challenges that ICNIRP and IEEE has for the EMF exposure limits. So surface area for millimeter wave is something which are, we can discuss more if you are interested, that maybe during the break. Time average quantification is something, because for higher frequencies, you need to limit it because of the temperature increase in shorter time. Peak values are something again. Volume shape is another possible missing scientific studies. That is my list, which I always feel that, okay, there is something that you need more to maybe study. Regarding compliance assessment standards, we have 3 organizations dealing with this: IEC, ITU, IEEE. So IEEE, we have TC34 dealing with that question, ITUT, ITUR, we noticed, and also TC106 is at ICC. And then just information exchange regarding the compliance assessment standard regarding 5G technologies. IEEE and IEC, they have jointly established a joint working group to develop compliance assessment standards, which was just actually established in October 2017. And there are going to be 2 joint working groups, one working on measurement, compliance assessment standard. By compliance assessment, it means that whatever product is on the market, you have to follow the protocol and the procedure to show the compliance of that specific device. And we are closely working also with ITUT Study Group 5 in order to transfer or harmonize compliance assessment related assessment procedures. So here are some challenges that we have in measurement side, which is listed here, and you can have a look at that. I want to be precise 10 minutes, so I pass this mic with.
Oh, thank you very much. Thank you, Jafar, for a most interesting talk. We will save the questions to the end. We will have a Q&A session. We have a little bit more time, so our 5G time frame has been extended a little bit. Thank you for coming back from an early lunch. I'm now going to introduce our remote speaker. So I'm hoping that Jack Rowley... oh, he's going to go at the end. Okay, he is going to go at the end. I was hoping to introduce someone from the future, but Jack can talk to us from the future at the end. So our next presenter is Mr. Haim Mazar, and I think you're represented on most ITU committees by the sounds of it. So a true expert, and I hand the floor to yourself, and we'll give you a 10-minute warning.
Good afternoon. Good afternoon. And this book, at least Mike and Jafar have thanks because they assisted me. And some of the figures here are from the book. Okay. So let's start. Okay, let's start. So workshop, ATDI coverage and EMF contours around 5G base station. And the down, where is the down? Mike? Okay, page down. This is page down. Okay, page down. Excellent. Session, what are the implications of 5G on EMF limits for 5G network rollouts? ATDI calculation method to present precisely exposure. And when I say precisely, I speak about meters. We have a DTM of 1 meter here in Poland. And predicting field strength level relative to national limits. I didn't write here ICNIRP because in United States it is different, and also here in Poland, as you understand. So we got many times this figure, and we have it in some reports of ITU and even in the application that Mike was developing. So from 1 hertz to 25 hertz, this is the 10 kilovolt per meter, 10 kilovolt per meter. And then we go to the 3 kilohertz, 87 volts per meter till 1 mega. I speak only about the public. This is 5 times more, and it is square root of 5 for the volt per meter. And here in 10 mega, the 28 volts per meter. 28 volts per meter. So when we speak here about 7, 5, 1 volt per meter in Krakow and so on, so it is very low. 28 volts per meter, this is the ICNIRP, and then we go up to the 61 volt per meter from 400 mega. So this is the frequency, this is the field strength, and field strength and power density are exactly the same when we are measuring. Next figure is taken from the K100 that Frederick mentioned today, RF measurement EMF to determine compliance. So you see here the antenna. And if the antenna is not looking down, so, and the person is here, what about the side lobe mainly in elevation? And we shall refer to it later. And if we go down, this is from Israel, from our Ministry of Communication. You have the transmitter, and here again, so we have to take into account at least the side lobe in elevation. And then we arrive to the power gain, EIRP, distance, field strength, and this is the field strength. It is square root of the EIRP, and the distance is here. So if we take 5 kilowatt EIRP, we speak about 900 mega, maximum downlink 100 watt, and antenna gain of 17. Those numbers are very, very, very typical. Unbelievable. If you take the GSM, you take the CDMA, you take the amps, you take the narrow amps, all of them, the downlink, it is 17 dBi, and it is in 3.4 giga and in 450 megahertz, because if you, Mike mentioned the 120 degrees in azimuth. So this is the 17 dBi, And 5 kilowatt is a very typical number. So ICNIRP in the 900 mega, it is 41 volts per meter, so 9.5 meter. So if you live 9.5 meter from an antenna in the main beam, in the free space loss, you are sure, according to the ICNIRP level. So this is a number, and NTT Docomo gave some numbers that are similar. What do we see here? If you remember, Filippo Binot mentioned this from the report that we have in Working Party 1C. This is figure number 6, EMF measurement to assess human exposure. We develop it with Rode-Schwarz measurements, and we do the analysis and computation. This was developed for Monaco, and those are the numbers. You see the 41 volts per meter general public and 90 volts per meter. So 90 volts per meter, here people can work. And if you go to the 41, people can live. So wall attenuation, we take into account wall attenuation. The transmitter is 30 meters above the roof. The mobile is 1.5, and here are the numbers that we saw again. So this is nice to show, and again, we speak about main lobe in azimuth, but not main lobe. We take into account the attenuation in elevation. So our next presentation is the 2D satellite view of cellular report. This is the same report. This is figure number 7. This was in Paris. Again, the 41 volts per meter in the 900. We see it now in 2D, and this is the downlink, 30 meters above as before. And you see that it's not too much frightening. Where is it frightening? Only when it is a little bit green and red. So it is about 20, 15, 10 meters from the base station. Now, let's have a look. So this is not frightening, Mike. You see here, this is the antenna. This is the main beam. But if we have safety zones using elevation antenna and tilt 0, if the tilt is 0, so those who are living below the antenna, they are the safest place. So if we have a school, the best place to put the antenna is in the roof of the school, because only side lobes will go down. People don't know it. They are afraid. There is an antenna on the roof of the school. No, the side lobe is very low below. So this is an issue that administration don't take into account. So we have to take using the elevation. Why I say elevation? I will explain it here. Even the azimuth is analyzed. Why azimuth? Typically, when you use 3 sectors, 5G and azimuth overlap is in 6 dB. So it is 120, but the 6 dB point is 120. And the plus minus 60 degrees, 3 dB point is in 45 degrees. So there is an overlap. And in azimuth, you can say that most of the population is in the main beam. And this is not the case for the side lobe in elevation. So I hope that the point is well taken into account and not to be frightening too much. And regarding frightening, when we make too many workshops, people say, you make workshop, there is a problem. If we don't speak about it too much, it's better. Think about it. And then we go to this figure. This is distance is using the 699 antenna. This antenna pattern in 5C, we approved it, and study group 5 2 weeks ago approved it in Geneva. And this is figure number 13, building impacted by point-to-point. People are afraid of point-to-point because the antenna are high and they are circular. What they don't know that the point-to-point is very directive. So even we have 40 kilowatt EIRP, only people who are in the line of sight, but people cannot be in the line of sight. The moment that you are in the line of sight, the signal will be obstacled. We are speaking about 20 giga, 40 giga, 50 giga. So point-to-point is not dangerous. And Orange Poland mentioned it in many contributions. So here we see what's going in Paris. Those are the 61 volts per meter that was already mentioned. A 10 giga ICNIRP levels are 61, C-scale also. Maximum power 2 watt, antenna gain 43 dBi. Again, those numbers are typical numbers. So 2 watt, it is a very powerful point-to-point. 43 dBi is typical, and the ERP 40 kilowatt. Free space loss exposure, 18 meter. So if you leave 18 meter, but in the main beam of the transmitter, and this is not typically the case. So this is 61 volts per meter, it is 18 meter. And if you take the 19.3 volt per meter, which is the occupational, those people who are working, it arrives to 57 meters. So this is again from the report that we are developing. And I call you again and again, please contribute to this report and contribute in parallel to ITUT. Now, those are related authors' presentation. And you can find it. And more important, what I write here, what are the questions to be asked? How exactly to calculate exposure contours by inserting additional losses? We cannot disregard the additional losses. We cannot disregard that if we operate 3.4 gigahertz, when we are inside the house, there is about 15, 18 dB attenuation of the wall. The same for the free space propagation. When we are in 1.5 meter above ground level, let's say that we are here, and let's say the base station is about, in Tel Aviv, every 60 meters we have a base station. Every 60 meters in average. So let's say in Warsaw it is not 60 meters, 80 meters. So let's say that from here we have a base station. I can assure you that from here to the base station, even though it is in 900 mega, it is no free space propagation. It's no free space. There are obstacles, there are multipasses, so we have to take into account propagation model. What about an antenna patterns? Now, if it is 80 meters from here and the tilt is 0, we can be in the main beam in elevation. And in the case also in azimuth. But we have to be specific. To conclude, I hope that I explained that ATDI has the tools in order to calculate with using DTM, very precise DTM. We can analyze. We make it in France. In France, they are very careful about schools, and they have a regulation. Not 100 meters from a school, you are not allowed to have a base station. So we developed it for France. It can be used also here. And I hope that in the discussion, we should discuss also my question. It was exactly 12 minutes, I hope, and even more. Thank you very much. Question. I ask all the time questions. Please ask me questions.
So we will do questions at the end. Thank you. And thank you very much for your presentation. So I think Kamil is up next. But I hope you're all paying attention, because under your seats there is an exam that you need to complete at the end. So I hope you were all paying attention. But so the next presentation will be from Kamil from Nokia. And the floor is yours.
Okay, thank you. Good afternoon, everybody. So what I would like to show you today is the impact how the 5G rollout can have on the RF exposure and other way around, how RF exposure can also impact the RF, the 5G rollout. Oh, just a second. Mm-hmm. Mm-hmm.
So we've lost our screen at the front too. I'm not sure whether that can be put back on. The screen over here is the one that's not working. I think it timed out. Yeah, I think it's... okay. It had a timer clock that said, maybe it's gone to lunch. Maybe the screen's gone to lunch. So if you wondered why we were looking blank before, we were watching this screen and then it's disappeared. Help. Yes. Oh, you didn't. Any closer? Right to go? Okay.
Yeah, okay. So let me go directly to the content. So most of us know the story of 5G and the components which will be improved by the 5G and the new solutions which will be introduced by the 5G. And what I would like to distinguish today are the two elements of the 5G relevant from the RF exposure point of view. And those elements are the small cells and massive MIMO. So small cells are present already right now in LTE. They help to improve the network capacity, but we expect that in 5G they will play even bigger role. Also in the new use cases in verticals like small cells for the private network. We also knew that the deployment of the small cells decreased the uplink transmit power, so the power transmitted by the user device, basically due to the uplink transmit power control mechanism. And recently we performed measurements which gave us the insight on the level of this reduction. So field measurements have been performed as a walk test within 100 meters around the small cell, real small cells. And the measurement results show us that the transmit power of the user terminal in uplink can be reduced by 9 dB in comparison to macro. So the UE, which is served by the small cell, has transmitting 8 times lower power than the same UE connected to the macro cell. And at the same time, we have better performance. So yeah, this already indicates how, let's say, this big deployment of the wide deployment of the small cells, which is expected also in 5G, can reduce the transmit power of the UE device and at the same time reduce the RF exposure. On the next slides already indicates that right now we already have the installation rules for the small cells. Depends on the EIRP of the small cell for the current limit of ICNIRP. But if the limits will be even more restrictive, if they are more restrictive, it means that we would need to have lower EIRP or less equipment per site. Then we have a worse performance. And to compensate this performance loss, we would need to introduce more sites, different sites with the new equipment, which generates the costs. and then also generates the delay in access to the network. The second aspect, massive MIMO, basically allow us to serve only active users with a dedicated beam for a duration of a call. So as we can see on this simple picture, the energy are only in those points are targeted only to those points in the space where we have a user, and those white spaces here are with the minimized amount of the energy in downlink. Yeah. So that causes less interference. And in this case, we also performed some analysis. Simulations have been performed according to 3GPP use cases from LTE-TR, where 3D channel model is defined for LTE. And maybe I will just mention about the main assumptions here. So in simulations, it has been checked the impact where we have a single UE per cell, 2 UEs per cell, or 5 UEs per cell with different connection times from 1 second to 60 seconds. And when we go to the simulation results, we got two sets of the results. The first one on the left show us what is the transmit power reduction in case where we have a single UE in cell served by different duration of the time. So let's take a look only maybe on the worst case. So this blue solid line is for the urban macro propagation model, and for the single UE per cell, which is active for 60 seconds. And we can see that for this case, we have a downlink transmit power less than 32% for 99 percentile of the simulation points. It's even lower for 95 percentile of simulation points. But if you take a look at the 100%, it's less than 35%. And the worst case, which is the reference point, here is the case where we have a single UE in a cell, which is served by 6 minutes, which is the time of averaging the measurements for the compliance with the RF exposure limits. Yeah. Similar situation is on the second set of the simulations, but here we are changing the number of the UEs per cell, which are served by 60 seconds. And of course, more UEs we have in the cell, then the total transmit power from cell has to be split, then the transmit power per UE is lower. So again, the lower power if we have more UEs per cell. Next slide just graphically illustrate the shape of the massive MIMO beam when we have a full transmit power and how it changed when we have 99 percentile transmit power considered or 95 percentile. Okay, so maybe we can already go to the conclusion. So 5G is introducing new possibilities, new spectrum, and further improve the spectrum utilization, even up to 98% according to 3GPP specification. However, more restrictive limits on RF exposure somehow decrease this performance of the 5G, either by lower transmit power, which leads to lower coverage capacity, or due to the increased cost of the deployment or delay in access to the network. And we know that our RF exposure can vary considerably in time, space, and it depends on the user activity and propagation conditions. But this can be checked by some statistical models, which can be further complemented by the measurement results. And part of that kind of assessment have been presented on these slides, and it shows that 5G can help to limit the RF power in the field, thanks to some kind of features which are assumed in 5G. Thank you.
Thank you very much. And you've done very well, even with the hiccup at the start. You're ahead of time, so we're on track for our 5G presentation. So, and you're happy, that's good. In keeping the presenters on their toes, Krista was meant to go second, but I juggled the order around. So Krista, I'd invite you to the stage or to the podium for your presentation. Krista Törnevik is the EMF manager from Ericsson. And should we use the PowerPoint? Is that better? We're playing with fire now. We're going to plug another presentation in.
Okay, we try to use the PowerPoint instead of PDF. So while waiting for that, yes, my name is Krista Törnevik, work in Ericsson Research in Stockholm, in Sweden. Closer. Can you hear me now? Okay. Which one? It's on the right. Too late. Hope the second. I use that point. Okay, then I'm set, I think. Yeah. Okay, once again, good afternoon, everybody. My name is Krista Törnevik. I work at Ericsson Research in Stockholm. I'm heading the area of EMF and health within Ericsson. We have heard a lot about the 5G and EMF so far during the day. I will try to add some more information about the possible implications of EMF limits on the deployment of 5G. So I use this one. Yeah, as we heard, 5G will introduce some challenges when it comes to EMF compliance. As we heard today, 5G will use massive MIMO and beamforming. And that will make, due to the dynamic beams that we will have in 5G and due to the very complex antennas, the EMF compliance assessments will be more complex. Also, with a potentially higher gain and higher EIRP of 5G, there might be larger EMF compliance distances than we have had for 2G, 3G, 4G. At least if we continue to use the theoretical maximum power, also for 5G, which I will talk about more, that maybe is not relevant. And so site design will be very important for 5G, especially in those countries using more restrictive limits than ICNIRP levels. Secondly, as we have heard several times now, we will, for 5G, use frequency bands above 10 gigahertz, up to 100 gigahertz, close to the near the millimeter wave range. We have standards in place on how to do EMF assessments in that frequency range, but there will probably be a need to do revisions of those standards when we start to use them because they haven't been used yet. And another challenge is related to the millimeter waves is that the limits, the ICNIRP limits above 10 gigahertz in the millimeter wave range are more restrictive in the near field compared to the limits below 10 gigahertz. Below 10 gigahertz, we have limits, basic restrictions, as we heard, expressed as SER levels. Above 10 gigahertz, they are expressed as power density levels. And those are more restrictive, which may result in larger EMF compliance distances for small cells than for 5G than we have had for 2G, 3G, and 4G. I will now give some examples how the RF exposure and the EMF compliance may look like for 5G products. So my first example is this is an Ericsson base station, 5G base station that we have launched. It's using the 28 gigahertz band. It's a small equipment. It's only 60 centimeters high. It includes 4 of these antenna elements, massive MIMO antenna elements, with in total 512 antenna ports, 512 small radios inside. The power is very low, less than 1 watt. Actually, the power of this one is less than the power of the mobile phones that Mike showed from the 1980s. With this product, we can serve hundreds of users with gigabit per second data rates. with less power than a mobile phone from the 1980s, 1990s. So it's a fantastic development. The antenna gain is 24 dBi, and the beam steering is plus minus 60 degrees in the horizontal direction and plus minus 15 degrees in the vertical direction. So this base station it has eight beams, 8 simultaneous beams. So what we did here is that we evaluated what the field strength distribution may look like in front of this type of base station. So this is the numerical calculations, but we have modeled every single antenna element here. And we have summed the field in a conservative way. And the pink area here corresponds to levels above 50 watts per square meter. That is the limit for occupational exposure, ICNIRP limit. This ISO curve here corresponds to 10 watts per square meter, which is the general public limit. So the compliance distance here in front is about 1.5 meters for this product. And it's about 70 centimeters high. And this is not an issue when for the deployment of 5G small cells. Normally not. But it's larger than we have for similar products for 4G products when we can use SCR assessments. Then the distance is typically like 20, 30, 40 centimeters. Now it goes up to 1.5 meters. And if you apply a limit that is 100 times of ICNIRP, like in Italy and here in Poland, the compliance distance will be 10 times larger. So then we talk about 50 meters, which can be a challenge, of course, even when deploying this type of small cells, 5G small cells. My second example is a 5G site for wide area coverage. So this is a 3.5 gigahertz massive MIMO 5G antenna mounted here on the rooftop. It has an EIRP of 72 dBm, and it's installed in this case together with 2D, 3D, and 4G. And here we have assumed that the power of all these antennas is at the theoretical maximum. So 200 watts for the 3G and the maximum for 2D, 3D, and 4G. And in that case, if you model and calculate what will be the compliance zone, the yellow area here is the compliance when you use the ICNIRP general public limit. So it extends about 25 meters from the antennas here. And for workers, about 11 meters. So this is a significant size of an exclusion zone, which can cause problems when deploying 5G. However, there is a solution to this. And that is a concept that has been introduced in 2 international standards. The latest version of a standard from IEC, 62232, about compliance assessment of base stations, and in an ITU-T standard, K100, where a concept of actual maximum power has been introduced. And that is, and we heard that mentioned in the previous presentation, that is defined as the 95th percentile of the maximum power. So instead of using maximum power for all of these antennas, which would be extremely conservative, these standards say that instead you can use the statistic. If you have the statistics of the power, you can instead apply the 95th percentile. And so many companies now are working on for massive MIMO antennas to develop statistical methods to determine what will be this actual maximum power instead of the theoretical maximum power. And we saw some results from Nokia earlier. And in Ericsson, we have developed a statistical model where we take into account the utilization of the base station, the scheduling time, the distribution of users connected to the base station, and also TDD. And that model has been published in a scientific journal. And this is one of the figures from that paper showing what is then the actual maximum power from a massive MIMO base station. And it depends on the size of the array. So, for example, for a typical massive MIMO array size of 64 elements, 8 by 8 array, the actual maximum power is only 22% of the theoretical maximum. So 95%, with a 95% probability, the power is less than 22%. So why should this actual power be used instead of theoretical maximum power? Yeah, the reason is that actually in reality, not all the power is used in a single beam over a long time, like 6 minutes, which is the averaging time in these limits. It will never happen in reality that you have all the full power in one beam over a long time. These beams will be dynamically moved in space and in time. Also, assuming 100% utilization of a base station is not realistic. It never happens in reality. We have measured in many networks that doesn't happen. And TDD will mean that some of the time the transmission is an uplink and part of the time in a downlink. So if you take that into account and use this statistical model that we have developed, you can see then that the size of a typical exclusion zone for a massive MIMO base station would shrink from about 20 meters down to less than 10 meters, which is more realistic when deploying 5G networks. Finally, I have 3 slides. I hope I can have time to show. This is a case study that we have developed together with a group of manufacturers and operators that is intended to be included in a IEC technical report that will be published next year. And we also intend to have it in a supplement, ITUT supplement that was mentioned earlier by Frederick, that should be ready also next year. So here we have modeled a typical 5G base station site. This is an urban rooftop installation with 3.5 gigahertz antennas and 128 gigahertz antenna, a small cell. So these to give wide area coverage and the 28 gigahertz to give high capacity. So if here we apply this statistical actual maximum power, and then you see that the compliance zone, the exclusion zone, if you apply the ICNIRP limit of 10 watts per square meter, looks like this. You can see the individual beams here. And the envelope of all the beams here constitute the compliance area. And it's about 10 meters diameter. And where the public can be, we are below the limit. So we are compliant when we apply this. But what will happen then if we instead use a lower limit, more restricted limit, like a tenth of ICNIRP, which is used, for instance, in India and in Switzerland? And we do the same calculation. Then we see suddenly that this compliance zone will be like 40 meters and about 20 meters high, which obviously will create some problems when deploying 5G in those countries. We either have to reduce the power or extend the antenna. And my final example is then what will happen then if you apply a limit that is 100 times below ICNIRP, 0.1 watts per square meter, like the limit in Italy and here in Poland. Then we suddenly see that the exclusion zone is huge, extends more than 100 meters from the rooftop here, and it actually reaches all the way down to the ground. So this will be, having this kind of limit with 5G will cause, I would say, big problems when deploying 5G, or even make it impossible, unless the power is significantly reduced. And then we, of course, will lose all the benefits of 5G with high capacity and so on. So that was what I had. Should I skip the conclusion maybe to save some time? Or, I'm okay. Okay, yeah, so my conclusions are then the EMF compliance may be a challenge for 5G, massive MIMO sites, if we assume this, if we continue to use the theoretical maximum power that we have used in the past. It's overly conservative and cannot be used. And we now have international standards in place that opens up for this use of the statistical actual maximum power instead. We have found in our studies that the actual maximum power for massive MIMO, for a typical massive MIMO antenna, is about 25% of the maximum power. And finally, in countries that have limits that are significantly below the ICNIRP limits, the 5G network deployments may be a big challenge. Okay, that was what I had.
That was very good to see the worked examples. Thank you, Krista.
Welcome.
I'm sure we'll have many questions in a minute. Thank you very much. We've got one more presentation from Dr. Jack Rowley, and this is where I have the pleasure of introducing a presentation from the future, because it's Tuesday here and it's Wednesday in Australia, and I have to transverse that future in a few hours. So, Jack, if you're online, we can see you on the screen there. Thank you for staying up and presenting back to us on Tuesday. And you're going to talk to us about the implications of RF-EMF exposure and the lessons learnt from 3G and 4G. So while you're still awake there, Jack, we'll pass it over to you. I think we're getting the presentation.
Yeah, thank you, Mike. I hope that you can hear me clearly. I'm sure that you will let me know if there's any technical challenges. I'll be asking somebody to advance. Great, thanks, Mike. I'll be asking somebody there to advance the slides as I go through. So if we get out of sync again, please stop me. So Mike said in his introduction, I'm speaking from the future. Well, I'm going to start by looking at the past and look at what we can anticipate will be the difficulties and challenges around 5G deployment based on some of the experiences in countries that have had restrictive limits and how that has affected 3G and 4G deployments. And before I get into the body of the presentation, I just want to thank once again the organizers, the ministry and the ITU for facilitating this remote presentation. Unfortunately, I wasn't able to be with you in person. So if we go to the first slide, please. And we look at the situation of Switzerland and a 3G case study. So Switzerland has got a limit of 5 volt per meter in terms of a mixed environment, 3G and 2G. I see Christina moving around. Is there an issue with the presentation, Mike?
I went to move to the next slide and something didn't quite work. So I think we have to scroll. Is that what we have to do, Christina? It's a PDF. Okay, so I'll scroll up. So we're on the case study for 3G in Switzerland now, Jack.
Great, thank you. So Switzerland has had this restrictive limit for quite some time. The origins are in terms of 2G deployments. They made an assessment about what they felt technically feasible as a allowable limit because of a requirement in their environmental legislation to consider precautionary approaches, which includes minimizing exposures from any sources, including, in this case, non-ionizing energy. That has had consequences on the rollout of 3G in Switzerland. The restrictive limits have increased the costs of deployment in Switzerland, and there was an analysis done in 2013 by PricewaterhouseCoopers, and they looked at the cost of deploying networks in Switzerland versus the neighboring countries of Italy, France, Germany, and Austria. And there were many drivers for those costs. Part of it related to the mountainous landscape, the fact that they've got many bordering countries, but the most important factor, 30% of the reason for the difference in costs and the increase in costs were the non-ionizing radiation regulations in Switzerland. And when they looked at, and this again is a 3G example, when they looked at trying to satisfy the consumer data demand and still supply those support those limit values, they found that the cost escalated even faster because of the restrictive limits. If we turn to the situation today, we've had CEO of Swisscom, one of the major operators, as you can see, say that with current limits, 5G deployment will be extremely difficult, if not impossible. The chief technical officer for one of the other operators in Switzerland said around the same time that they do not turn on the full capacity of some of their existing 4G sites because they can't at the moment because of the limit values. If we turn to the next slide, please, which is a case study in Brussels. And this is a 3G, 4G transition case study. So Brussels, even though it's a very small country, it's a federal country. There's 3 distinct regions, with the Brussels capital being one of them. And for reasons of local politics, they adopted a 3 volt per meter limit, but they didn't just adopt this as being the overall limit. They then effectively divided it among each of the operators, so it was shared, so that no one operator could, if you like, use all the limit for any particular installation. And that had some significant problems for 3G deployments. And when the time came for 4G deployment, the telecoms regulator, the BIPT, looked at the implications of this Brussels limit for 4G deployment and said it would be a serious obstacle. And they were right. 4G was deployed in all of Belgium, with the exception of Brussels initially. And the operators made it clear that it just was not feasible to deploy with that restrictive limit. And after about 12 months of discussion, a new compromise was arrived at, which changed the 3 volt per meter number, managed to keep it the same, but now applied it on a per technology basis, so a significantly higher level of transfer each of this, which meant that the Brussels could finally get 4G deployments. But even at the outset of that deployment, one of the operators said that this was just a temporary solution, and they could see that in the future this would not be sufficient. And we had this situation come to an unfortunate highlight in 2016, when there were the terrorist attacks in Brussels on the airport and on the trains. And one of the operators reported in the aftermath that in order to satisfy the consumer demand for making calls, for accessing video, for connecting to their families and friends and be reassuring, they allowed their antennas to transmit at levels that would have exceeded the Brussels limit. Following that, there was an inquiry organized by the Brussels government, and they have now had a formal agreement whereby the operators are allowed to increase exposure or transmission power if required in certain situations. But this still is really only a band-aid. As the last headline shows on the right-hand side, the capital of Europe loiters in a mobile dead zone. Brussels still has some of the worst 4G coverage in Europe, and the operators are talking now about 5G not being possible, which is something of an irony, as I was just noticing today that there has been some political agreements around the desire to roll out 5G across Europe. We could have the similar situations we had in 4G in Brussels, where it will be everywhere, but not in Brussels itself, where the European Commission has gone. If we turn to the next slide, we're looking at a case study in Italy, and this slide and the next one are both from a GSMA analysis that we did in 2014 with the support of our members. So limit of 6 volt per meter. And the bar chart on the right is showing the percentage of sites that are available to co-site a 4G antenna. So the orange bar shows that if you're dealing with the ICNIRP limits, then 100% of existing sites could potentially be available to put a 4G antenna on them. If you go to the smallest purple bar, that's the current or Italian limits based on peak power, and only 6% of the antenna sites are available for sharing. In something again of a political technical compromise, Italy has come up with this idea of an average power over 24 hours as the basis for assessment of compliance with the limit value. Zenon would probably say that's got very little or nothing of relevance to any of the ICNIRP thresholds, but this is a way to provide some relief without changing the limit value number. And so in that case, you get with the black bar chart where about 40% of sites are potentially available for co-location. The important message from this is that if you can't co-locate at an existing site, it means you need a new location. And so we see the proliferation of antenna sites and resulting costs, and also resulting visual intrusion as a result of these restrictive limits. If we go to the next slide, slide 5 is the case study from Poland, again from the same report. Here they've looked at it in a slightly different way. What they've defined is a series of site configurations. So site configuration A is just with one technology, 3G at 2100 megahertz, and site configuration F is with 6 mobile technologies, GSM, 3G, and LTE in different bands. And they've looked at, in order to be compliant, what percentage of sites have to have their output power restricted or reduced. And we've got blue bars for rural and small areas, town sites, and then yellow bars for the cities. So if we just focus on the city situation, because of the restrictions in Poland, if you've only got one site, one technology, the configuration A, then only about 1% of sites are affected in terms of having to be down powered in order to be compliant. If you go to the configuration F, where you're trying to put multiple technologies, maybe this is a rooftop types installation or a tower, where you've got maybe several services going into one antenna, almost 2/3 of power of antenna sites have their output power reduced. If you reduce the power, the only way to replace that coverage is to put in additional sites, additional antennas. But even when you do that, as there was analysis done in Romania, while you may be able to get back the external coverage, you still struggle to get the same level of internal in-building coverage. And we know that people use their mobile phones and their mobile devices more than 60% of the time indoors. And the percentage seems to be increasing. So people are not using them in their cars or their streets necessarily, but they're also using their homes, and they expect to have that connection, whether it's for work or for pleasure. If we turn to the next slide, slide 6, this is looking at RF-EMF levels in public areas. So one of the reasons I put up this slide on the next slide is presumably the idea of having restrictive limits is to have lower exposure for the public. And this was a study where measurements were done in Belgium and Switzerland, which we've already talked about, have restrictive limits, and the Netherlands, which has the ICNIRP limits. And their overall conclusion was the exposure levels were highly variable, both spatially, so within an area, and considerably between different areas, so between the center of the city or the more suburban areas, and also between cities. So there were some situations where Belgium showed lower average levels, but there were other situations where the Netherlands showed lower average levels. And so you had this highly variable total exposure, and importantly, there's no indication from this study that the lower limit values in Belgium or Switzerland mean that there are lower exposures to the public. You see a similar sort of result in the next slide, which is based on a study that I was involved in. We published back in 2012, collected data from surveys done by national authorities or by universities and publicly made available either through the scientific literature or on government websites for 23 countries all across the world, European, North American, Asian countries. And there's a whole lot of information on this slide, but I'm just going to focus on a couple of aspects of it. So if you look, there's a line, a dotted line across the middle of the chart, which is the global weighted average, and that was about 5,500 times below the ICNIRP levels. And you see a scatter of results above and below, but represented by the colored shapes. And you also see a large spread between the minimum and maximum values that you observed in different countries. I then highlighted the 3 countries that we had data for, which had restrictive limits, Belgium, Greece, and Switzerland. And you can see, again, in this way of analysis, that the levels that the public are experiencing are pretty much the same as they're experiencing in any of the other countries, which are virtually all ICNIRP or similar numbers. So if the rationale for having restrictive limits is reducing exposure because there is a public health benefit, it's not happening. The exposure is not being reduced by having these lower limits. So some conclusions, and I've made this presentation short because being at the end of the group, I thought we might have less time. Just three key points that I wanted to make. First off, and most importantly, the restrictive limits do not appear to result in lower public exposures. So there is no inverted commas health benefit. What it does have the practical effect of making site sharing difficult, thereby increasing the number of sites and increasing the cost of deployment, and also delays the deployment of services. And we've seen that specifically in the example of Belgium and the city of Brussels. And of course, that means you miss out on the associated benefits. So thank you. My short presentation is done. Thank you, Mike.
Well, thank you, Jack. And that was that was an excellent presentation given remotely, looking back at the past from the future. So we have a few minutes for questions, and this is, I'm Jack. I'm hoping you can stay with us for a few minutes. There might be some questions.
Certainly will.
So we've just seen some really good examples of what's to come. We've seen two case studies, or two examples from one from Nokia and one from Ericsson on their current tests and on the test networks, and the fact that we're not using maximum, the network design doesn't use maximum power. To be most efficient, it uses power levels below maximum, and that's very encouraging. We've seen some predictions, and Haim has his book, and I'm sure you can sign copies of it in the coffee break. But there's you were looking at realistic exposures and the attenuation through buildings, and not scaring people with those big green figures. And Jafar, you looked at the compliance standard. You looked at the comparison of standards and what we need to do in the standards world. And we've just had Jack give some really good reflection on the experience in 3G and 4G. And when you see that collection of case studies that Jack just presented, that's quite revealing. So I'd like to open the floor for questions, because I'm sure you've saved some questions. So if we start off, who would like to start us with the first question? And you'll have to use a microphone. And if no one has the first question, then maybe I'll ask a question. But does someone have a question? We do have one from the front. Thomas.
Hello, this is Thomas Baumüller speaking, mobile and wireless from HiCheck. Jack, you mentioned in one of your, on the last slide, that the actual exposure does not reduce if you have lower limits. Do you also have something to say about the perception of the public when you lower the limits? How do they perceive the actual exposure when the limits are lowered? Thank you.
Well, we certainly know from two lines of evidence. So we know from studies done by psychologists in laboratory sort of situations that any measure that you take for whether you label it precautionary or because you say you want to be more protective, seems to confirm people's fears that there must be a problem. And so those people who see or have references to those sort of policy approaches show more concern. We see it on a larger scale in terms of the European Commission Eurobarometer survey, where when you look at the last one was done in 2010, and if you look at the average level of concern across the EU, all the countries showing higher concern have got some sort of precautionary measure, whether it's instructions to users, restrictions on citing, or restrictive limits. They all have higher concern, and countries that have lower concern have got science-based limits, they've got clear compliance procedures, and they've got clarity of information for the public. So yes, the evidence seems to be quite strong that not only does reducing the limit value make it more difficult to deploy networks and not change exposure. It also seems to be associated with higher concern.
Okay, thank you, Thomas. Do we have another question in the room? Oh, wait, Frederick.
Thank you, Frederick Lewicki. Jack, this presentation was really, really interesting, and in my opinion, we will really encourage you to send contribution to ITOT with your conclusions, because even in EMF guide, we have no such statement that more restrictive exposure limits does not mean lower exposure. So it is really important to have such statement widely spread for general public. So thank you very much for also some background, measurement background is very important for that. Thank you very much. It is only comment.
Thank you very much. And we have a question at the back.
Ignacy Święcicki from the Ministry of Digital Affairs. Thank you very much for this very interesting panel. I have a question which is slightly a follow-up to the first question. You mentioned that in those countries which have stricter limits, there are more, the perception of exposure is higher. But is there any correlation between that average exposure and average throughput that's achieved on mobile phones? Or the difference is only in costs of network deployment?
Okay, so I think that's probably one for the manufacturer. So the question, if I can clarify, was is there any correlation between an increase in throughput and lower exposure? Is that what you're... Oh yes, so lower limits and reduction in throughput. Now there has been a study in France where they looked at small cells. And I think you mentioned that, Kamil. Did you want to have a look at that question? Because I know that they've been looking at this very issue at the moment.
So I think that the answer is rather not, because if the lower limits applied, the operators anyway are trying to improve the network performance by additional equipment in new sites and etc. etc. So it only increases the costs of the network layout and delay to access to the network. But operators anyway are trying, this is my understanding, operators anyway will try to somehow ensure that the network performance, the throughput will not be worse than in other places in the world where we have a higher limits. That's my understanding.
Okay, maybe I can just add to that. In France at the moment, in Paris, the ANFR, so the French regulator, are looking at a case study with small cells. So they're looking at coverage, throughput, and power levels without small cells, and then the addition of small cells. What they've found is that when the small cells are deployed, as we've heard before, the connection distance is much shorter, the connection is much better, and you get a higher throughput, and the background level doesn't increase. So you're getting a direct correlation with the ability to build infrastructure, increase the throughput, and that means that the level from the handset will also be reduced, and you've got more data, more people using devices, and the background levels or the EMF levels have remained the same. Now we can put you in touch with the ANFR are publishing these results, so it would be, we could share that with you. But I have a question. Jafar, you wish to add to that?
Besides what you said, maybe it's the time to emphasize on the importance of realistic exposure, because compliance, when we have a base station and we want to assess for the compliance, we use the maximum nominal, which is not realistically used. So that is one part of the story. The other part of the story is that, okay, the average use of field levels, they are, let's say, 1% or 5% of the actual, which means that at the end, these stricter limits are about the same as what is for the other cases, which means that here we have the importance of using the realistic exposure approach rather than non-practical nominal maximum level.
No, that's a really good point. We often get asked, as a network operator, we often get asked, can we come and talk to a community group And can we show them what the levels are? And we will take the best measurement equipment and we will demonstrate that. And they're often well below the maximum predicted. And they're well below because the network is performing well and we don't use these maximum powers. But I'll just ask one question, then I'll go to the back. So I've got... an observation from Haim, sorry.
The observation is this. We heard that there will be a contribution to ITU-T regarding the 95 percentile. So instead of using the maximum power, we shall arrive to 20% of the power. And for sure, even in Poland, the distance will be appropriate. My concern is that we heard ICNIRP, and ICNIRP are not with the operators or the providers. If we, in IEC or ITU-T, invent new way to reduce the power, not by reducing the power itself, but reducing the way that we assess it, it may be dangerous because people will say, again, the industry and the operators come and try to make some changes. So this is a point that we should be very cautious, and we have to work with ICNIRP, with WHO, with IEEE, in order that all of us will agree about the new way to refer to the power. And for sure there is a power control and there are side lobes, and for sure if the antenna is smart antenna, it will pinpoint and not all the time. So this is a concern that we have to discuss. Thank you, Chair.
So you raise a really good point, and I was going to ask this question before, but in terms of network experience, and I've seen a presentation from Ericsson and Nokia where they've trialled exactly this, Haim, where I think one of the examples was the Silverstone racetrack and other examples in Europe where you've tried this and you physically measured the power. So Krista, could you let us know about what your experience is in reality when you go and measure sites like Haim was talking about?
Absolutely. First, I would like to say, Haim, that this has nothing to do with manipulating with limits. No. Not at all. Of course, we will apply ICNIRP limits or the national limits. This has to do with doing assessments in a more accurate way, improving the accuracy. Because today, when we assume theoretical power for several minutes for all antennas, it's totally unrealistic. That never happens. And to answer your question then, Mike, is that we have done measurements together with operators in a number of countries for 2G, 3G, 4G, and now also 5G, and seen that if you measure 24 hours a day, 7 days a week, look at the statistics, there is in many cases not a single 6-minute interval where we have power levels above like 50% or so. For 4G especially, the power levels we have seen are extremely low, like on average 10%, 95 percentile like 15, 20, and the absolute maximum we have seen in networks is like 30%. So these numbers are just reflecting reality. That's what we're trying to include. And now recently there have been also measurements on massive MIMO antennas that will be used for 5G that the Vodafone has. That Mike talked about. And it confirms that these models, statistical models that we have developed actually are correct. The real power, in the fraction of the power used in a beam in a certain direction is in the order of 20% of the max. It's never more than that. So in order to improve the accuracy, we need to start to apply this kind of models.
Okay, so there is a question at the back. Thank you very much.
Hello, Jolanta Karpowicz from Central Institute for Labor Protection. Thank you very much for excellent technical presentations. But let me show you a very difficult problem with the perception of the message from the meeting. Of course, I understand everything from my personal experience, but the message for people who are not experts. From one side, you said that new technology needs very higher limits than we have now in Poland, 7 volts per meter. In parallel, we learned what we know very well from measurements, that the real level of exposure now, it is not related to the limits, it is related to the technology, and in every country is similar. Let's say 1 volt per meter to have a simplified message. Further information we learned is that new technology needs, let's say, twice higher level of exposure. It means 2 volt per meter. So why you try to push for the higher limits? I think that more realistic is to think about more realistic compliance tests method, what Jafar said. Because from one side we are talking about real level of exposure, which is in the real condition of the use of the system, probably 99 and 90% of time of the use of the system will be without of maximum power transmission, because people will not use service every time. So this maximum is absolutely theoretical value, which will probably never happen in the real world. When you will try to push changes of the limits, the result will be against the technology. I think that it's really time to think about a modification of the message for the public. It is just from my experience, more than 20 years of experience in that field. Hello, Jack. Thank you.
Okay, so...
Well, Yolanta, nice to see you.
Yes, go, Jack. Yep.
I understand that the point that Yolanta is making. This is always a challenge. Communication is a challenge around this topic. So to distinguish, I think, first off, 2 situations. The first one is the levels that I'm presenting are the levels that are average in the street. The levels that the presentations from Ericsson and Nokia were talking about is the compliance zones. And those are the areas that an operator has to have control of, has to be able to manage access to those areas. So having unrealistically large compliance zones means a problem from a siting point of view, and you can't co-locate, and there are all the other issues. So that's one aspect of it. And I agree with Yolanta, and I think all the other speakers have talked about the need to have more realistic approaches to compliance assessment. But the other side of it, to me, says that, as Zenon said in his presentation, the limits should be based on the science. And if the science drives towards that the number X is the value that's protective of health, then that's what we should be using. And you can use it for an analogy for the sound level. So we know that if you stood beside the jet engine of a jumbo jet, you would damage your hearing very quickly. And so we have a standard in place that provides protection for hearing. And then we've got lower levels for sleeping areas and for otherwise. But we don't set a threshold that says that everybody has to whisper. And that's what we're trying to do here in the RF if we move away from not setting the limits on the basis of science. 2 further observations I'll make. I've been involved in this for a long time too, Yolanta, and I do believe that there is a hardcore group of people who are very concerned, but I think that they are in the minority, and that's what we see in terms of the level of media interests in this around the world. And so I think we need to anticipate that there will be opposition and concern, but there's a necessity perhaps to challenge that opposition as being unfounded and to use it to address the challenge correctly. Because I think ultimately the science is right. And we have seen countries, and Mike comes from a country where Australia raised the limit by a factor of 5 in moving from the old limits to the ICNIRP limits back in the early 2000s. And the industry and the government anticipated that there would be a lot of media and negative concerns around that. But a very fair process was put in place. independent group that evaluated the science, that made the recommendation. It went through several rounds of public consultation where everyone had a fair opportunity to put their voices across. And ultimately, the government made the decision that move to international limits was based on science and therefore in the best interest of the country. So I think, yes, it's a challenge, but it's not a challenge that we should necessarily run away from. Thank you, Mike.
Yes, thank you, Jack. And I think we might wind up for the, unless there's any other questions, we might wind up for the coffee break in just a moment. But just to pick up on that point, because you asked, the question you've just asked is a very fundamental question that a lot of countries ask. And it comes back to a couple of things Jack said, and maybe I can just use this in closing. Fundamentally, we have to base health standards, whether it's ionizing radiation, non-ionizing, it's other aspects, have to be based on science. And we've heard the science update, and irrespective of what industry want, what communities want, the scientists will give us the exposure guidelines. And I've been asked by family and by others, what's the responsible approach? And we talked about that earlier. So we're not health experts, that's why we defer to ICNIRP and others. If they set the health exposure standards, then our challenge and the right, in my view, the right community response is that we design testing standards at the IEC and ITU to follow the latest science and follow the latest technologies. And just as the technology is getting better, the standards are getting better, and we're applying these new test methods because we go out and we do the readings and we do the assessments and we find the power levels, because of the new technology, are lower. So our testing methods need to match that. So the responsible approach from an operator's perspective, if I wear another hat, is to design our networks to work the most efficient so that you get the coverage and the connections you need using the lowest power. And then countries and regulators and governments need to say, what is the most appropriate standards for our country? And our advice is to go with the health agencies, but that's up to a government because they've got to balance connections, community. So that's just sort of, there isn't, you'd like a follow-up? And that's my personal view.
Okay, thank you. Very important comment, but please look into details on what we have from the science. Most of experiments with the cell cultures, animals, and epidemiological observations, they refer to the average exposure during the time. So it is the other argument that compliance tests should also refer to the average exposure in time, not the maximum, because when we use different metrics of the exposure for the compliance tests and different metrics for the exposure which is taken in limits, in the science for limits, the message for non-experts is completely non-understandable. It's better to have limits for average from science and to show to the public that for any reason we use 20 times lower average, also average value for the everyday practical use, it is much better message for the public that say that we have from science something and compliance test is for the same level and for maximum. Nobody will understand it.
Thank you. You wanted to say
not something, just to respond because that's related to the compliance assessment. In the compliance assessment standards, every procedure has to be absolutely clear because those protocols are used to assess the compliance of a product. And regarding the realistic exposure, I would remind that also exposure limit setting bodies, they use the realistic because this is going to be used in the real world, in the real life. Now, what the realistic exposure or values, power levels, they are, if you are calculating that, let's say you choose 99 percentile. or 95. That's an agreement. But that is statistically clearly calculated and scientifically a correct way, so nobody can understand in a different way. And that's why what we are using regarding maximum nominal power, if it does not exist in reality, there is no sense of using that. That's why the realistic approach now ICNIRP is introducing or has already introduced, and what we are seeking here in compliance assessment standards, that's because we have to be absolutely clear, and when you have a statistical analysis and rationale for those numbers, 95, 99, whatever, it has a clear understanding for all the users and the developers of the standards. So that is, I mean, there is a clear scientific basis, and it is not open to interpretation. Everybody would understand in the same way. And for compliance assessment, we have to be absolutely clear.
Ladies and gentlemen, would you thank the panel of experts that presented this afternoon?